Welcome to Calculus. Today, let's do a recap of what we just saw from the intro video, learn some new additional concepts, solve some examples, and then get a clear idea of some of the first very basic rules of calc. So let's begin. So let's review our key findings of differential calculus, also known as calculus about derivatives. We know that in physics terms, the derivative is the rate of change. And we also know that the geometric meaning of a derivative is the slope of the line at a specific point. The derivative, rate of change, and the slope of the line, all of these are just different names for the same thing, the same concept. We can find the derivative by using the average rate of change, the rate of change over an entire time interval, and then use the limit operation and then make the length of the time interval smaller and smaller and smaller, approaching to a size of 0. And bam, we can find the instantaneous rate of change at the time of our interest. In our last lesson, we saw that a function has three representations: the table, the equation, and the graph. Now with the graph, we can find the derivative through a limit operation of a tiny rise over the corresponding run. That is, remember in the last lesson that a picture is worth 1,000 words? That's why when we can use geometry, shapes, and lines to describe something in math, well, we just go ahead and do that. Now, let's look at an example of applying geometry to math. So, when, let's say, for example, if we have a displacement function called xt equals a times t squared, where a is a constant number representing acceleration and t is time, the derivative of xt, the vt, the velocity function, is 2 times a times t. Now, let's use some geometry to represent all of this with graphs. So we have the xt displacement function graphed out, this guy right here, and the vt velocity function also graphed out. So as you can see here, for this point on the xt curve, it has a certain steepness to it. And then on the same x-axis point on the velocity graph, there is a certain value for this point. For this second point over here, it seems like things are a bit more steep. The second point has a greater steepness. And then on the same x-axis point on the velocity curve, there seems to be a higher value. And then for this third point over here, this point seems to be even more steeper, and then the same point on the x-axis for the velocity graph seems to have an even higher value. So the velocity's value is the same thing as the steepness of the slope on the xt graph. So when the slope is steeper, the velocity will definitely be bigger. Here's the graph for all the slopes of the displacement function, which is the straight line to a t, which is what we just talked about over here. Now, with our recap, we can start with some fun but also very useful examples. The focus is to practice around with how of our understanding with derivatives and how to use derivatives correctly. Now let's talk about an important property of differentiation, and differentiation is the process of finding the derivative. This property is called the linearity property, which is something not to be confused with linear equations. Those are kind of like two different things. We're focusing on the linearity property for now. So differentiation satisfies two specific properties known as homogeneity and superposition. So as you can see here, we have a function called x of t. And we're using differentiation to find the derivative function, x of t prime. Now, here's where this homogeneity thing comes in. So if our function, if we have another function right here called a times x of t, and we do the derivative of it, and by the way, a is any finite real number, the derivative is just a times x prime of t, with the same a as a multiplier. Nothing happens to the a. It's like if it gets moved aside for a second, the differentiation process happens to the function xt, and then a returns to its original row position in this whole thing. This property is called homogeneity. It is extremely weird, but this is just how things work in here. Now, let's look at the next property, the property of superposition. So we know again, when we do the derivative of xt, we get xt prime. Yeah, but here's the thing. Now let's say we have an x1t plus x2t, basically two functions added together. We try to do the derivative of this thing, and we end up with this. The derivative of the first function plus the derivative of the second function. This is what we end up with. The sum of the derivatives of the two little functions is the derivative of the sum of the two little functions we began with. Basically, we just did the derivative of each individual function and then have everything all together in the end. Now this whole weird ordeal is the property of superposition. I know superposition is a very strange name for this strange concept, but again, that's how it is. So yeah, differentiation is shown to both follow the property of homogeneity and superposition. This differentiation thing now has the property of linearization, which is something that both fulfills the properties of homogeneity and superposition. Now, let's do some examples for derivatives, just for some practice and a good little recap. Okay, so for the first question, okay, what is the derivative of xt equals 60 times t? Well, the derivative is the rate of change, and it seems to be that the rate of change is 60. So our derivative is 60. Okay, so for the next question over here, what is the derivative of xt equals 120 times t? Well, we do the same thing as last time, and our derivative is 120. All right, I think we are getting a good idea of what's going on already. Now, time for problem number 3. What is the derivative for xt equals t? Well, if you think of it this way, t is also t times 1. So the derivative is 1. And that's the thing. Any function that just equals to one variable and like nothing else will have the derivative 1. So now we know that in general, if xt equals a times t, where a is a constant number, then the derivative will be a. Now, things get a bit different in this problem. So what is the derivative of xt equals t squared? Well, surprisingly, it isn't 1 or anything like that. The derivative is 2 times t. So the way to solve this, okay, the way to solve this is that you take the number that is the same number as the exponent, okay, and then you multiply it to the variable t, and then you get another number that is the exponent's number, but minus 1. And then set this number as the new exponent. And then this is the answer. This is your derivative of this. Okay, let's try another one. What is the derivative of xt equals t to the third power, t cubed? I see that the exponent number is 3. So my answer will be something like 3 times t something something. I know that 3 minus 1 is 2, and then that should be our exponent, and here we go. This is the answer, 3 times t squared. The derivative is 3 times t squared. Okay, let's try another one. What is the derivative of xt equals t to the 10th power? Well, the answer is going to be 10 times t to the power of 10 minus 1 equals 9. 10 times t to the power of 9. And that is our answer, our derivative. So in general, the derivative of t to the nth power, where n can be any natural number, the answer, the derivative, is n times t to the power of n minus 1. And there we go. Okay, now let's get to this one over here. What is the derivative of xt equals 5 times t squared? Well, when we are doing the derivative of this, we can use the homogeneity property that differentiation is equipped with. So basically what we have here is that we have 5, a constant number. We move that 5 aside for a second. And then we just do the derivative. Now we have t squared, and then we do the derivative of that, and then we know the derivative of t squared is 2 times t. So the end, and then now we move 5 back into the picture, and our end result is 5 times 2 times t. And then we also know that 5 times 2 is 10, obviously, and then our final answer is 10 times t. And that is our final answer, 10 times t. That is our derivative. Okay, now, what is the derivative of xt equals 6 times t to the third power? So first we move 6 aside. We know that the derivative of t cubed is t to the third power is 3 times t to the second power. So then when we move 6 back into the picture, it's 6 times 3 times t squared. And then our final answer will be 18 times t squared. And then this is our final answer. The derivative is 18 times t squared. Now yes, final question. What is the derivative for this equation right here? By using that strange property that's called superposition, we can just do the derivative of each differentiation for each individual part or term. So let's see, this one right here, the derivative should be just 10. And then for this one right here, we know that the derivative of t squared is just 2 times t. So, and then when we move 5 back into the picture, it's just going to be 5 times 2 times t. And then 5 times 2 is obviously 10. And then this is our final answer, 10 plus 10 times t. And that right there is our derivative. Perfect. We have recapped derivatives. Now let's have a recap on integrals. In physics, we know that the velocity is the derivative or rate of change of displacement. But displacement is the integral, the antiderivative of velocity. We also know that in geometry, the integral is the area under the curve, or more specifically, the area between the curve and the x-axis. We will get to that later. Finally, we know that the total sum of very thin slices of an area under the curve can approximate the real area under the curve. And we can make those thin slices infinitesimally thin to a point where their sum can represent the true area. This is how calculus can be used to find the integrals of functions. the integral operation is represented by this weird big S symbol, as you can see here. Now let's do some examples for integrals, just for some good practice. All right, so for the first question, what is the integral of this x prime t equals 2? Well, the integral is the opposite of the derivative. We see that the function given to us, this x prime of t, and imagine it as a derivative. And our goal is to try to find a function that this derivative belongs to. The function we're trying to find is, in fact, the integral. Okay, we can imagine that this x prime of t equals 2 as a velocity function. We're trying to find a displacement function. Since 2 is our rate of change, this is our derivative, in this case, the velocity, then 2 times t must be our answer. Since velocity multiplied by time is the displacement in this kind of ordeal, the integral, the answer to this problem seems to be 2 times t. But hold up for a second. We don't know the initial displacement. We don't really know what the initial starting value is. We were only given this velocity function, this x prime of t equals 2, the thingy that decides the slope, but that's about it. So since we don't know if the initial value, what the initial value is, we add a number called c. C representing a constant number that can be any real number. It could be anything. So our real final answer to this question is x of t equals 2 times t plus c. This is our integral. Let's check out the next question. What is the integral of x prime of t equals 14? Well, we do the same thing as before. We can treat this 14 thing right here as a rate of change to some other thing, and we're trying to find that other thing. So our answer for this one is 14 times t. But, oh shoot, I forgot to add c. Yeah, guys, when it comes to these indefinite integrals, here's the thing. We are doing indefinite integrals this whole time. So this is the integral symbol, which is this big weird S thing of, let's say we're doing this question over here, 14, and then we have dx right here. So this is an indefinite integral. And definite integrals right here, they have these weird little numbers. And remember I said that the integral is like the area between the x-axis and the curve? So with a definite integral, you're doing the integral only from between two specific points. You're finding the area under the curve between two specific points on the x-axis. But now we're just doing indefinite integrals where you're doing the area under the curve for the whole thing right here. So when it comes to these indefinite integrals, we don't know the initial condition. We don't have any basis for that. So we don't know the initial value and we cannot say what it is. We don't know if c is equal to 0 or not. So just in case if c is a number that isn't 0, we have to add c. So our final answer is 14 times t plus c. This is our integral for this question. Okay, now for this question. What is the integral of x prime of t equals 68? This nice function right here. Well, as we knew from the stuff we did from before, the answer is 68 times t plus c. Okay, this is when things get a bit more interesting. What is the integral of x prime of t equals 2 times t? Well, remember, Doing the integral is like doing the derivative backwards. We know that the derivative of t squared is 2 times t. So, and there we go. We got our answer. If 2 times t is the derivative of t squared, then t squared is the integral of 2 times t, except this is an indefinite integral, so we also have to add c. Our final answer is t squared plus c. Plus c. Okay, time for this question. What is the integral of x prime of t equals 3 times t squared? We knew from the rules of differentiation earlier that the derivative of t to the third power is 3 times t squared. And so our answer for this question is t to the third power plus c. This is our integral. Alrighty, so what is the integral for x prime of t equals t? Well, remember that the integral of 2 times t is t squared, right? Okay, we can imagine that this x prime of t equals t thing is actually just a half times 2 times t, because 2 times a half is 1, and whatever times 1 is still the same thing. So these two are like equal in this case. So we do the integral of 2 times t and get t squared. And don't forget to have that remaining 1/2. So our final answer is a half times t squared plus c. This is our answer, our integral. What is the integral of x prime of t equals 4 times t? So we have to divide a 2 from 4. So now we have like a 2 over here, and now we can get like a 2 times t, this guy right here, and then we can integrate this and this will become t squared. So our final answer for this question is 2 times t squared plus c. This is our integral. What is the integral of x prime of t equals 6 times t squared? Well, we know that the derivative of t cubed is 3 times t squared, and vice versa, as the integral of 3 times t squared is t to the third power. By that logic, see that 6 over here? We can divide that 6 into 2 and 3. So now we have a 2 times 3 times t squared. When we do the integral, we know that 3 times t squared, the integral of that is t to the third power. And then we have this remaining 2. So basically, our final answer is 2 times t to the third power plus c. And woohoo! Last final question of the day. What is the integral of x prime of t equals 9t squared plus t? Well, from all the things we learned, we know that the integral of 9 times t squared is just 3 times 3 times t squared, and the integral of that is 3 times t to the third power. And we also know that the integral of t is a half times t squared. So our final answer will just be 3 times t to the third power plus a half times t to the second power plus c. And there we go. There we go. So yeah, from all the examples we did, I think we learned some basic rules of derivatives and integrals. There are more rules to those things, but for now, let's focus on the ones we already learned. So feel free to take a screenshot and review these. Yeah, and also, by the way, a is a constant number, and n right here, our little exponent right here too, is also a constant number. FYI. Now, let's talk about some subtleties, some anomalies with derivatives and integrals. They will be explained and resolved in future videos, but for now, we have to learn to be aware of these subtleties. First, we know that from the list of rules that the derivative of t to the power of n, let's say the derivative of t to the power of n is n times t to the power of n minus 1. Now, what if that n equals 0? First of all, our answer will be 0 times t to the power of 0 minus 1, which will equal to 0 times t to the power of negative 1, which equals to 0 times 1 over t. So basically, t to the power of negative 1 is just 1 over t to the power of 1. All right, so you probably think this thing right here equals to 0, but that isn't really always the case. What if the t in this case is equal to 0? It will be something like 0 times 1 over 0. The thing is, you cannot divide by 0. You cannot really do this. So this is kind of like a peculiarity right here, like an anomaly. So all I need to say for this one is that you may have to be careful inputting some numbers for functions. Sometimes a function can have an extremely sharp turn or a break, a discontinuity. You can measure the rate of change of parts of the function that aren't a sharp turn or a discontinuity, but you cannot really apply a rate of change, derivative, onto those sharp turns and discontinuities. So these functions cannot be differentiable as a whole. So that's something to watch out for as well. Finally, we discussed this before in the intro to calc video, but this is a little review on that. And here's the thing. The integral isn't the area under the curve, actually. It's more of a area between the curve and the x-axis, which is what I mentioned from before. Just like that. This highlighted stuff right here is the area. And then when you add all these areas together of this function, you get the integral of this function. We say the integral is under the curve when the curve is usually above the x-axis, when the curve is usually above the x-axis and thus the area is positive. And when the curve is under the x-axis, as you can see right here, the area is negative. So when we add these two areas together, it's actually this area minus this area. So that's something to watch out for also. So yeah, that's the review for the basic stuff for calc. And I honestly hope you guys enjoyed this vid and found it helpful. Bye guys!